For more than 200 years, astronomers have been wondering what asteroids actually look like. They believe that these primitive rocks have been concealing countless secrets for billions of years. From the far-flung reaches of space to laboratories on Earth, scientists are trying to unlock these secrets. Asteroids are time capsules that take us back to the formation of the solar system and the creation of Earth. Unfortunately, laboratories have only access to tiny fragments of asteroids that have burned up as they have fallen through Earth's atmosphere. We know how to send probes into space, but they have a limited number of instruments on board, which is why the major space agencies are determined not just to explore asteroids, but to bring hermetically sealed samples back to their labs. In order to choose which asteroid to explore, scientists need to locate a suitable target and characterize it using telescopes. Thanks to the first basic telescopes, humans discovered the presence of asteroids in the 19th century.
Let's assume we have the Sun here. We have the Earth orbiting the Sun. We have Mars a bit further out, and all the way in the back there's Jupiter, the largest planet in our solar system. Asteroids come from the main belt, which is between Mars and Jupiter. They circle the Sun.
Most known asteroids come from this area. Their presence is linked to the formation of our Sun.
The solar system formed about 4.5 million years ago out of a big cloud of dust and gas which contracted. When it contracted, these dust particles started to grow to what in the end became the planets. But there was an intermediate step. We call those planetesimals. These are objects from meter-sized, maybe to hundreds of meter-sized, and were left over after the formation of the planets.
Asteroids are sometimes known as minor planets. They are the pieces left over when the solar system formed. From time to time, these fragments wander into our world. Shooting stars are asteroids that enter our atmosphere and disintegrate. If they hit the Earth's surface, they are called meteorites. Meteorites are prized by collectors, who look for them in areas such as deserts where there is little vegetation. Their composition is also of great interest to laboratories. They search for something unexpected in a rocky world, organic compounds such as amino acids.
If you look at the outside of meteorites, you can see that as they enter the Earth's atmosphere, they can experience some heating and melting. But the interior components of the meteorite that were shielded from the heating upon entering Earth's atmosphere, those are what we're interested in when we're looking for amino acids.
Every form of life on Earth contains amino acids, so asteroids are scientific treasure troves.
Amino acids are the basic subunit that make up proteins. And when we study meteorites and we look for organic compounds like amino acids, it gives us clues as to what types of chemical compounds meteorites may have deposited onto the surface of the Earth at or near the time of the origin of life.
Meteorites and asteroids are ambassadors from a bygone world.
Meteorites are particularly interesting because they contain a chemical record of the solar system.
So laboratories collect meteorites to understand the composition of asteroids, or to try and prove that life on Earth is extraterrestrial in origin.
There are many building blocks of life that have been found in meteorites to date, but there are still some that have not yet been found. And some of our future research and the future research in the field will be focused on finding those missing links in the building blocks of life.
But scientists have realized that while meteorites provide clues, they are not enough to confirm where life on Earth originated.
We get an opportunity to investigate what the materials of the early solar system were like. We can collect material from the surface of Earth and we can examine that material, but that material has been subjected to a lot of temperature over a very long period of time, which has processed and changed the original ingredients that made the early Earth. It's sort of like baking. You can start out with a set of original ingredients, mix them together and put them in the oven, and when it comes out of the oven, you have a delicious chocolate chip cookie or a delicious piece of banana bread, but you don't know what the original source ingredients were like. And the same is true with the Earth. We can see what the Earth is like today, but we don't really know what those ingredients were like when the Earth was first forming.
Since meteorites on Earth cannot provide enough information, scientists dream of going direct to the source.
If we really want to understand these asteroids, we need to go up and see them. We need to get up close and personal. So we need to take space missions to these asteroids with wonderful cameras and other space instruments in order to look at them, to characterize them, and to understand their unique evolutionary history.
By the end of the last century, we had still not seen these minor planets up close.
Their gravity is very weak, so the behavior of matter is very different to that on Earth. So if we want to understand the behavior of the matter, or to understand what they're made of, we have no choice but to go there.
Message received. In 1996, NASA sent the Near-Shoemaker probe on a mission towards an asteroid.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Liftoff of the final Delta II, launching nearly 3 decades of science research and exploration missions, lifting ISAT-2 on a quest to explore the polar ice sheets of our constantly changing home planet.
Despite being a world first, it was a low-budget operation, and the engineers worked from a tiny control room. After a great deal of hesitation, NASA chose the probe's destination, the asteroid Eros. The American Space Agency shared its observations in real time with thousands of impatient scientists.
On February 14, 2000, it reached Eros, and it was really extraordinary, because Eros is the goddess of love. And on Valentine's Day, a small probe made contact with this asteroid.
Up until that point, humans had only ever explored planets and their moons. A mere 21 miles long, Eros was the smallest object that humans had visited in space.
Every day we received images from the probe, which was the start of a year of extraordinary discoveries. One of the first things that hit us was that the surface of Eros was covered in a layer of sand, known as regolith, like the surface of the moon. Another discovery that we made on Eros with the NEAR probe was that it was a kind of brown color. And that's interesting because it gives us some clues to its composition. We noted that there were no small craters on it, and the only explanation that we could find was that when craters are made, Eros is so small that it vibrates and the regolith moves and erases the traces. So these characteristics are really clues to what happened in the asteroid's past.
At the end of the mission, the team made a bold proposition. One of them remembers this decisive moment that would change the course of asteroid exploration.
We've now been for a year at Eros, collecting about 100,000 images. We'd like to see what the asteroid looks like very close up. So the decision's been made to go and approach the asteroid and land.
It was an extremely risky gamble. Near Shoemaker could not be piloted directly, since each instruction sent from Earth took more than half an hour to reach the probe.
We need to plan the sequence very carefully from 100,000 miles. There's not going to be any opportunity for a human in the loop to change anything. So the whole event needs to be carefully choreographed down to the surface. And then, is the spacecraft actually going to continue to be able to transmit data all the way down to the surface, including when it interacts with the surface? Something we don't really know, but will be very exciting to find.
The engineers were working completely in the dark.
We're actually approaching obliquely across the surface to maintain power with the sun and then being able to downlink all our data straight back to Earth. And as we're coming down, we're coming up and over a crater rim. We can actually see some pretty large boulders as we fly in. And finally, we're ending up in a ponded area. These are regolith-dominated craters filled with fine-grained material. And the last image was cut as we approached. It was taken about 120 meters above the surface because it takes some time for an image to be collected and downlinked back to Earth. One big concern is the loss of power. If a solar panel hits the surface or if the spacecraft rocks over, we may lose some of the data that we might be able to collect at the surface. Remember, this spacecraft was never intended to land.
From the far reaches of the solar system, the news arrives at last.
But we have got all the pictures are still coming in. This is the first time that any spacecraft has landed on a small body.
We've finally touched down with the surface. This is the first time we land a probe on an asteroid.
For 2 weeks, the probe analyzes the ground, concluding a year of observations and the first ever in situ analysis of an asteroid. It amends the observations made by telescopes and discovers an abundance of olivine and pyroxene, common components of volcanic rocks on Earth. This discovery confirms that our planet's mantle is made up of the same minerals as asteroids. The success of this mission will serve as an inspiration for other countries.
The NEAR mission was the first human venture to explore an asteroid using a space mission. It showed that we could land on an asteroid and that such an achievement would provide information that is impossible to obtain from Earth. So, in the end, it caused a stir that opened the way for missions by other space agencies.
These space agencies and their contractors are now challenged with developing probes to meet scientists' new expectations.
We can learn so much from bringing asteroid material back to Earth. So by returning a sample, we will have an opportunity to study in our labs in incredible, exquisite detail what the early ingredients of the Earth were, and those ingredients that led to water on Earth and the formation of life on Earth.
The first sampling mission was launched by a country that had played little part in the space race, Japan. In 2003, the Hayabusa mission set off towards the asteroid Itokawa.
5、4、3、2、1、0。
Based on their knowledge of Eros, scientists expected Itokawa to be fairly compact and covered with plains of regolith. Taking a sample should be straightforward, but a rocky road lay ahead for Hayabusa's team.
This mission was like an Indiana Jones mission. It was absolutely crazy, full of adventures, surprises, and suspense.
When Hayabusa arrives at Itokawa, the team discovers that the asteroid is covered in rocks.
For scientists, it was great because it's a new challenge understanding how it's possible, but for engineers, it was a nightmare because the idea was to get close to the asteroid, land on it, take a sample, and bring it back to Earth. And when there's a lot of rocks, that becomes very complicated.
To prepare for this smooth touch and go, the probe has to survey this strange cluster of rocks in detail.
So the probe continues its approach. It stops at a distance and starts mapping, exploring and discovering that, in fact, we knew very little about asteroids. And then we start to understand that it's going to be very complicated to carry out our mission.
Any obstacles taller than 1.5 feet risk damaging the probe when it lands. In order to map the area more precisely, the engineers decide to send a rover to the ground.
The problem is that when we deploy the rover, its trajectory doesn't take it to Itokawa, and it misses the asteroid. That shows us that these objects have so little gravity that there is no room for error. We need to be really, really precise when we start an operation because gravity doesn't pull us. There's not enough attraction, and so you have to launch at the right moment.
Despite all these challenges, the engineers managed to determine a possible landing site. Nearly 200 million miles from Earth, Hayabusa must make its own independent decisions. The pilots deploy visual markers to help the probe to guide itself.
5 メートル、4メートル、3メートル、2メートル、1メート
The
ル。
sampling attempt is underway. Unlike Near, Hayabusa cannot end its days on the asteroid. To protect it from mishaps, it is programmed to halt its descent in case of anomalies. And that's precisely what happens. Itokawa's rocky surface causes the optical navigation system to abort and return to orbit.
AOCU スタートディセント 0x0001 送信します。210
Second attempt.
The probe descends. We see images of Itokawa getting closer. There's huge suspense in the operations room.
5メートル4メートル3メートル2メートル1メートル
And then
Et puis là,
nothing.
plus rien.
The probe appears to have bounced on the surface and landed on the edge of its solar panels. Nothing goes to plan. It should have taken a sample and returned to orbit. Immediately, the control room sends instructions for taking off. The message will take more than half an hour to arrive at the probe, but there is no way of knowing if it has been received.
西山君。はい。
All contact has been lost. But after 2 months without any news, the engineers finally tracked down Hayabusa. Spinning in the vicinity of Itokawa. The probe is damaged, but it is instructed to begin its long journey back to Earth. Meanwhile, scientists try to assess the composition of Itokawa. Theoretical models show that Itokawa should be an aggregate, in other words, a pile of rubble held together by microgravity.
Itokawa actually revealed that a body as small as 100 meters across can be an aggregate, which is precisely what our simulations showed.
Based on detailed pictures taken by the first in situ missions, planetary scientists use equations to retrace the history of asteroids back to their origins.
What was shown in the calculations is that when you break a large body, you start to pulverize it into very small fragments of 100 meters at most.
And for those who question the accuracy of their calculations, scientists use a space gun.
To confirm our numerical simulations, we compare them to high-velocity impact experiments in labs on Earth.
This gun shoots metal balls at ceramic targets and reproduces the incredible speeds that asteroids travel at, over 18,000 miles per hour. These experiments provide the first confirmation of the physics of these impacts, but they don't explain what happens to the debris in space.
So when the asteroid shatters into small fragments, our simulations show that they then tend to follow each other and reagglomerate to form clusters.
The first observations from the NEAR and Hayabusa probes shook up scientists' preconceived ideas about asteroids. It is now believed that most small celestial bodies are not uniform blocks, but collections of rocks resulting from collisions and their frenzied dance around the sun. Unfortunately, space gun experiments cannot completely validate the models.
In labs on Earth, we're limited by the size of targets. We use targets that are about 1 centimeter wide, so even if they are validated at this scale, the calculations are not completely reliable at larger scales.
If the Hayabusa probe comes back to Earth with dust from Itokawa, it would help refine these models and understand the origin of the rocks that make up asteroids. In 2010, Hayabusa finally returns to Earth. The probe is programmed to disintegrate in the atmosphere above the Australian desert.
This 7-year adventure came back to Earth with its samples, even though the mechanism itself didn't work.
When it crashed into the surface of Itokawa, the probe managed to take a few precious grains of asteroid dust. They are distributed to various laboratories around the world.
One interesting finding about Itokawa was that both indigenous and non-indigenous material appears to be on asteroid Itokawa. And this is indicative that perhaps material came from a different solar system body and was deposited on Itokawa before the Itokawa sample was analyzed.
The analysis of the dust from Itokawa shows that small asteroids are capable of reforming after a collision while also gathering the rocks that caused the collision in the first place.
Small asteroids are made up of aggregates that were formed from the destruction of a larger body in the asteroid belt.
This discovery puts to rest the earlier simplistic representations of monolithic asteroids. Thousands of fragments produced by the destruction of larger asteroids group together through mutual attraction, producing a population of small asteroids. Now that the shape and nature of asteroids is better understood, space agency contractors can develop suitable sampling probes to search for organic compounds. At the end of 2014, the Japanese space agency JAXA decided to launch a second Hayabusa mission to a carbonaceous or C-type asteroid. To this scientific first, the Japanese threw their doors open to international cooperation, even inviting foreign scientists into the control room.
Hayabusa was a technology demonstration mission, but this time the aim is scientific. The idea is to bring back samples from an asteroid that is potentially rich in carbon and therefore in organic matter, in order to answer major questions such as, did asteroids bring the material that allowed life to emerge on Earth?
The Hayabusa 2 probe heads towards an asteroid called Ryugu, named after a mythical fish that inhabits a magical underwater palace.
In the control room, we received regular images taken by the probe during the approach phase. At first, Ryugu was just a small dot, but gradually we noticed its perfectly regular and symmetrical shape, like a spinning top. This shape came as a surprise to us, because up till that point, it was just a theoretical model.
Ryugu is a relatively small asteroid, measuring less than 3,000 feet in diameter. According to some models, it should be made up of a collection of rocks, but for the first time, there is almost no regolith.
When the probe arrived in June 2018, we discovered a world that was completely bizarre compared to what we expected.
As we get closer, we realized there was no flat area to land. It was very dark. The ground was very chaotic, very uneven.
The probe studies Ryugu for 10 months in order to map it precisely and to choose the best sampling area in the rugged terrain. Another surprise is that the asteroid is a range of unexpected colors.
We have bluish material and reddish material. The red material is the same composition as the blue, but it was simply on the surface and was exposed to the sun for longer. The blue material is younger because it has less exposure.
The asteroid is actually darker than shown here, but the colors bear witness to the history of the formation of this pile of rubble. To prove this, Hayabusa 2's most daring challenge is to obtain rock samples from beneath the surface, away from the influence of the sun's rays. The surface rocks must be removed with what astronomers call an impactor.
In April 2019, a small box fitted with an explosive is deployed.
Before it explodes, you have 40 minutes to get Hayabusa 2 to shelter on the other side of Ryugu.
The explosive sends a projectile weighing 2 kilograms at 2 kilometers per second onto the surface to make a crater.
We made a crater 20 yards in diameter and 9 feet deep on the surface of the asteroid. It was a total success, a world first.
All that remains to be achieved is the part that Hayabusa 1 failed. Obtaining a real rock sample of an asteroid.
We need to find a place where we can go and collect material from the subsurface near the crater without rocks. We can see there is no area more than 5 meters across where there are no rocks. We ask ourselves, how are we going to land, knowing that the landing precision is about 50 meters? The Japanese are obliged to completely revise their descent strategy so that their accuracy is reduced from 50 meters to 5 meters. We are 300 million kilometers from the Earth, and a satellite has to be guided so that it hits an area to within 5 meters, which is absolutely incredible. There is a major discussion amongst the team to decide if they go ahead or not. But the Japanese are not afraid of anything, and after careful consideration, they decide to go ahead with the collection.
We decided not to go to the interior of the crater, which is very deep and therefore dangerous for our probe. Instead, we decided to harvest at the edge of the crater, 20 yards from the center, where we found a surface that was very flat.
When you're in the operations room, you realize how concentrated you have to be because the slightest error could be fatal. That's a big celebration. The Japanese are really happy. It's the first time it's been done. Once again, we feel like we're creating the history of asteroid exploration.
Our aim was good. We landed just 3 feet from our target, and we were able to collect samples from the asteroid's subsurface.
Hayabusa 2 starts its long journey back to Earth, its great success making up for the relative failure of Hayabusa 1. Yet it was this pioneering mission that inspired NASA to give the green light to OSIRIS-REx, a sample return mission to another carbonaceous asteroid called Bennu. Science has to avoid making generalizations based on one specific case. Instead, it must cast a wide net.
By sampling as many asteroid samples as we can begin to collect a cornucopia of material that we can analyze and investigate for organic compounds important for life.
The mission exploits the fact that Bennu passes close to Earth every 6 years. On September 8, 2016, OSIRIS-REx sets off on a long round trip.
2, 1. And liftoff of OSIRIS-REx, its 7-year mission to boldly go to the asteroid Bennu and back.
Despite running simulations, each asteroid is different. The probe is prepared to survive the worst and will face the unexpected.
We had to make some assumptions based on what we've seen on other asteroids. We've made some estimates about what we thought the surface of Bennu might be like.
The OSIRIS-REx mission, designed at the same time as Hayabusa 2, only had Itokawa as a reference for predicting Bennu's properties.
We expected that the surface of Bennu would be covered in a fine-grained material, much like the lunar regolith on the surface of the moon. This was supported by the observations that the science teams had done of Bennu before launch. They used ground-based astronomy, radio astronomy, and infrared imaging to deduce the surface material on Bennu.
But telescopes cannot compete with in-situ observation missions.
When we got to Bennu, we found to our surprise that instead it's covered in a lot of rocky material, and it's a much rougher surface than we were expecting.
Like Ryugu, Bennu is a collection of dark rocks that make sampling complicated. To work out the best landing area, numerous scientists from around the world collaborate with NASA and watch the first pictures beamed back by the probe. This pile of rubble takes them all by surprise.
We are in the OSIRIS-REx control room with the whole scientific team, and we discover that Bennu is what we call active. In other words, there are particles ejecting from its surface. It was like Wow. On the one hand, it's really exciting, but on the other, it's really worrying.
So why is this happening? Is there something to do with the composition of Bennu, what it's made of? Is there maybe water or something else that's driving that? Or is it due to some type of static electricity that's forcing them off? Or maybe it's something to do with the thermal regime, the thermal cracking, if you will, and preventing sending particles out. We just don't know.
The OSIRIS-REx sample return mission must deal with these unexpected events.
We're having to redesign the mission as we fly it, which gives us a whole new challenge for mission operations we haven't had before.
Like the Hayabusa missions, the aim of the American mission is to take samples from the surface of the asteroid. But they are hoping for a larger quantity by using a mechanism called TAGSAM.
During the spring of 2019, we did low-altitude flybys of the asteroid. We're getting images with incredible resolution that tend to confirm that we have particles that seem to be as fine as we want them to be in order to capture samples.
To take samples, the operators must lower the probe onto a sloping surface the size of a tennis court, wedged between several large boulders, while at the same time dodging flying rocks.
You have to match rotation, you have to match the slope angle, because that may not be nice and flat. It also may be very rough. So these are all things that you have to take into consideration when you land on the surface of an asteroid and take a sample. It's done very quickly. It's a matter of a few seconds in each case, and then come back up. But it's a very challenging operation.
First attempt, October 20th, 2020. More than 100 million miles from Earth. No human intervention is possible despite all the obstacles that could put the mission in jeopardy. At first glance, the collection attempt seems successful. But Bennu has one more surprise in store.
The OSIRIS-REx sample collection is in a way a victim of its own success, since the surface reacted very differently from what was expected, and we collected much more than expected. So we try to close the cylinder containing the samples, but we can't do it, and we see particles starting to escape.
If even the smallest piece of grit jams the hermetic seal, the whole sampling mission is doomed to failure.
It was very scary because we have to close this cylinder to put it back in the re-entry capsule. We should have measured the mass we collected, but we can't because it requires an additional operation and we don't want to waste time. So we rush to take the cylinder and try to put it in the capsule and close it.
Success. With more than 7 ounces of rocks and dust on board, OSIRIS-REx has collected 4 times more than the Hayabusa 2 mission. While one probe leaves an asteroid, another approaches our planet. In December 2020, Hayabusa 2's sample capsule enters our atmosphere with a collection of rocks from Ryukyu. Once again, these samples are dispatched to the best laboratories around the world. They will finally be able to provide answers about the contribution of asteroids to the appearance of life on Earth.
We expect to find long carbon chains, which means that complex organic compounds like those found on Earth would naturally occur in space.
Carbon is one of the most common elements in the universe and is capable of forming stable molecules. In the future, we can expect to see carbonaceous samples returning from the 4 corners of the solar system, beginning with those from Bennu.
And now we're just waiting for the samples to come back very anxiously. It's almost like Christmas time. You don't know what you're going to get, but hopefully you will have a nice package. We won't know that until the samples come back.
These missions provide evidence that asteroids contain carbon elements and water, the essential ingredients for life. The water they hold is chemically closer to that of our oceans than that from most comets, suggesting that life on Earth came from asteroids rather than comets. Over the last 2 decades, these missions have changed our approach to asteroids. We no longer see them as gray stones. We now know that these clumps of rocks are a diverse range of solitary travelers. The water they contain has shaped our planet. Today, we are entering into a new relationship with these minor planets.
We have learned a great deal from the space exploration missions we've carried out, and this opens the way for private companies to start exploiting.
After sampling missions, asteroid mining in situ or near Earth may seem like the next logical step. Some contractors and space agencies already have their eye on their rare metals or plan to extract ice from the asteroids, which could then be turned into a valuable resource.
That's rocket fuel. If we get the technology mining and extracting the water, think of these asteroids flying around the solar system as actually fuel depots where you can actually go. So that makes Mars exploration much more available, maybe other destinations in the solar system.
Today, the economic viability of asteroid mining still has to be demonstrated. For the moment, its interest lies in extending our capacity to explore the solar system rather than for commercial ends. Who knows? Perhaps the next sample may bring an unexpected Christmas gift.